Okay, welcome everyone. We heard an excellent talk at lunch by Emily Leiner, and she will tell us some more now. And before that, I was asked to mention that there will be an event taking place today at 2 to 4 p.m. about augmented reality open house, and it will. I guess there is information about it on the website, but I don't see is it online or? Sorry? P257. So anyone interested is welcome, and Alisa is the organizer. We also had yesterday a very nice forum to the public with the Harvard bookstore that, again, Alisa coordinated, and Kelsey Johnson was there. Featuring her book. Where is Kelsey? Oh, over there. And we will hear from Kelsey as well. One last thing I wanted to mention. Just a few days ago, I visited Richard Branson's home in Necker Island. It's one of the most beautiful places on earth. And I asked him when he when his life ends and he reaches heaven, how would he notice it? Because he already lives in heaven, so to speak, on earth, and he said, I never get used to it. So that's a good lesson for life. Never get used to heaven. So we'll hear first from Emily about what are these sub-subgiant stars. That's a portion of the Hertzsprung diagram that she did not touch during her ITC colloquium. And after that, we'll hear from Kelsey Johnson from the University of Virginia, who will tell us about the importance of O in the sciences. I guess O is appreciated in other regimes, right? Like religion, but in science, not so much. Then we'll hear from Hongping Deng from Shanghai Astronomy Observatory. Hongping, where is he? Yeah. And he will tell us about Meshless finite mass method applied to planet formation, subtleties in resolving subsonic turbulence in distorted accretion disks and beyond. And finally, we'll hear from Rafael Luque from the University of Chicago, who is over there. Who will tell us about the water world opportunity. We look forward to that. Emily.
All right. Thank you. So today I'm going to talk about what are these sub-subgiant stars, and this is work that I have done mostly with Aaron Geller, who is also at Northwestern, as well as some of my students at the Illinois Institute of Technology, Jonah Wilkes, Elaine Bai, and Eden Peskovic. So first off, what is a sub-subgiant star? This is a color magnitude diagram of the open cluster M67. And you see there's like a main sequence, there's a giant branch, and there's these two kind of strange stars that fall almost a full magnitude under the base of the subgiant branch in just a region that is not populated by any type of stellar evolution track. And these have been in this color magnitude diagram since the first color magnitude diagrams of M67 were made decades ago, and people kind of dismissed them as probably field contamination. But we have excellent memberships at this point from extensive kinematic studies, Gaia parallax. These are true members of the cluster, and so we need to figure out what they're doing down there. The subsubgiants in M67 are some of the first that were discovered, but they're not alone. In 2017, Aaron and I made a catalog of papers that had found sub-subgiants in clusters, both open and globular clusters, and we found about 70 candidates. And the candidates have some things in common. They're usually observed to have X-ray emission. They have H-alpha emission. They have photometric variability. And we don't have orbits for most of them, but the two sub-subgiants in M67 are both short period binaries. One has a period of about 3 days, the other has a period of about 18 days. So in short, these sub-subgiants seem to be very magnetically active giant stars. Possibly many of them are binaries. There have been many kind of theories put out about what could make a sub-subgiant star. Some of them are sort of rare dynamical interactions, but really I want to focus on kind of two broad categories. One is, have these stars lost mass? If you just lose a ton of mass from a giant star, you can make one that's pretty underluminous compared to the cluster. And then the sort of Occam's razor idea is that we know these are magnetically active stars. Perhaps strong magnetic activity on its own can create very underluminous stars. And so the idea here is these are stars on the subgiant branch. Their core is kind of contracting and releasing a lot of luminosity into the envelope. And if you have a strong magnetic field, that can actually suppress the convective energy transport. This has been, hypothesized to be at work in like M dwarfs, where we see a lot of radius inflation for active stars, pre-main sequence stars. Perhaps the same mechanism is just at work in these very convective giant stars. So we were a little bit limited by the small sample size, and most of the sub-subgiants were in these distant globular clusters where we couldn't do a lot of very detailed work. But with Gaia, we actually took a sample of known active giant stars, they were all photometric variables, and put them in a color magnitude diagram to just test, are these just field active giants also below the giant branch? And indeed, we found that they were. So the color magnitude diagram on the right shows the sample, and about 25% of them actually fall below a 14 gig-year metal-rich isochrone. So this is like the most ridiculous model. It's a very metal-rich, very old star. But just for the sake of argument, that's about the reddest isochrone you could possibly make. And these 25% of these stars are fainter and redder than that isochrone. And my student Elaine has done some nice work actually looking at metallicities for these stars in Gaia. And if you put an appropriate isochrone of the right metallicity on it, that's 14 gig years, you actually get about 75% of them fall below the isochrone. So something seems to be at work that does make these active giants in the field underluminous. We actually found among this field sample many eclipsing binaries, which is exciting because it actually gives us a chance to measure fundamental parameters for them and answer this question, are they very low mass, they've lost a lot of mass, or are they not? And we actually found this one system that's a double sub-subgiant, two sub-subgiants in an orbit of about 30 days. And we got a radius fit to it and fit some stellar evolution models. And what we find is that given the mass and radius we measure from eclipsing binaries, a standard evolutionary track with a mixing length of 1.8, which is the solar calibrated value, does not fit where these stars are. You actually need to lower the mixing length to about 1 to fit these stars. So it kind of supports the idea that convective energy transport is less efficient in these giants. And if you're just saying all giant stars have the mixing length that we calibrate to the sun, that's wrong. And you're going to have wrong evolutionary tracks. So that's one result. The other question we wanted to look at were most sub-subgiants are radial velocity variable in these samples. We didn't have enough sampling to actually get orbits for all of these stars, but for about 60 of them, we had 3+ observations and could assess if they were binaries or not. And my student, Jonah, did a really excellent job of looking at actually the amplitude of the RV variation, that's on the x-axis, and simulating a sample of binaries to see what distribution of orbital parameters is this distribution of kind of sparsely sampled radial velocity amplitudes consistent with. He also plotted, these are where we have 7+ observations. So these amplitudes are getting very close to reality, whereas the crosses are quite undersampled. So he simulated a model where all of the stars are actually in tidally locked binaries, where the rotation period and the orbital period are the same. And that fits actually fairly well, but not perfectly. The best fitting model is actually that these are short period binaries, but some of them are eccentric. So these are periods out to about 30 days, fit pretty well. And what is definitely ruled out is that this is just a normal field binary population or single stars. That would be the red curve, and that's not what we see here. So most of these sub-subgiants are short period binaries, and they are likely rapidly rotating due to tides. They might not be perfectly synchronized, but they're spun up by tides. But about 20% of the sub-subgiants are not consistent with short period binaries. They're either single stars or they're quite long period with orbits of hundreds or thousands of days. So to answer my question, what are these sub-subgiant stars? Most of them seem to be rapidly rotating subgiants or early giants in which convective energy transport may be inhibited by just the strong magnetic field. Most of these are rapidly rotating because of tidal synchronization. They're short period binaries, but not all of them. About 20% of these seem to be rapidly rotating for some other reason. And our best guess right now is that either means they are stars that have accreted during mass transfer or they're mergers. And that's it.
So Emily, the effect of the companion could also deposit some heat into the envelope. Would you be able to infer how that affects the evolution of those?
Yeah, that's an interesting question. For the most part, these seem to be very low mass companions that are not that hot. But we haven't looked at that. That would be an interesting thing to check.
I mean, through the tidal effect, not the irradiation.
Yeah.
Please.
So you said that in these stars, the convection length seems to be shorter and they are less convective or less efficient. Transport is less efficient to convect.
It's one idea, yeah.
Would that not make the superficial magnetic field less intense rather than more intense? Because for the dynamo effect, you need convection to bring the magnetic field from the center to the surface.
So your question is like the actual magnetic field strength of these stars?
Well, would that mechanism not tend to make them less magnetically active than more magnetically active?
Well, in general, the giants are not supposed to be that magnetically active. They're also not rapidly rotating, but these seem to be quite active. They're flaring, they have spots, they emit X-rays. So, the magnetic activity is definitely there, and it seems to be, enhanced because there is a companion there in most cases. So there's always energy going into the star from the tides, spinning it up. But yeah, I don't know.
Any other comments, please?
So would you say that these stars are magnetically active because there's an enhanced dynamo, an internally generated magnetic field due to the rotation? So
That's the idea. Yeah.
Otherwise, they're like subgiants.
Yeah. Yeah, so they're just stars that are subgiants or very early giants. They're not super evolved stars that are they're much more rapidly rotating than a typical giant because of these companions, or in 20% of cases, for some unknown reason, they're just really rapidly rotating.
Well, if there are no more questions, let's thank Emily.
All right, let me put this on. I'm fighting to keep my voice this week, so if you wouldn't mind pretending that I sound like a normal human, that would be great. So I get that this is a little bit of a weird talk for an ITC lunch, so I appreciate you indulging me. This is something that I would say actually feels more interesting and more important than talking about my own science. And I want to take these sort of 10 minutes to give kind of a pitch and a call to action for all of us in the room. I do a lot of weird stuff back at the University of Virginia, but one of the things I do is a lot of, I think, interesting interdisciplinary work, and this is coming out of an interdisciplinary project that I'm doing with folks in a bunch of different disciplines, including religious studies and psychology. And I think it's very important to us as scientists. So again, thank you for indulging me in this probably odd duck talk that you don't normally get. Okay. What I want to start out with, just to set the stage, is there is an actual psychological definition of awe. I think the word awe is used in many different ways, and there are many words that are adjacent to awe that mean similar things, but in terms of psychology, there's a working definition that is really important for everything else I'm going to say. And since this definition was put on the playing field in 2003, studies of awe and the importance of awe have really taken off. You've probably heard like TED Talks on it, and there are books on it, and lots of articles, and it's just really erupted almost exponentially as an area of study, which I think is really interesting. So when we talk about awe in terms of psychology, right, you could define it however you want elsewhere in your world, but in terms of psychology, awe is defined as when you simultaneously experience something as being vast, and that could be physical or conceptual or ideal, whatever it is, right? I don't want to overprescribe what vast is, and simultaneously, you have the need for what is called accommodation, which comes out of Piaget and educational psychology, and the need to revise your mental schema, meaning whatever it is you're experiencing doesn't fit in your brain. You don't have a framework to put it in. And when you experience those two things simultaneously in terms of psychology, you are experiencing awe. Okay, the reason I'm up here talking about this instead of my own science is I think this is really important for all of us, and actually kind of existentially important for the future of the human race, if I want to be a little bit hyperbolic. So there have been lots of studies on awe, and many, many results have come out of it. And I just want to give you a little bit of a sampling so you get why this is important. So this is a laundry list of reasons I would argue experiencing awe is really important for us as scientists, it's really important for us as teachers, and it's really important for humanity. So even if I just take the top and the bottom things on this list, we know from studies in psychology that experiencing awe is really important for creativity, which I would argue is important for science. I hope you're with me on that. It's also really important for, we go to the bottom of the list, curiosity, which I think is like the bedrock of science. So I just want to give you a little bit of motivation, and then in what follows, I'm going to give like this rapid fire overview of some of the studies that have come out, so you can just actually just see the data and see where some of this is coming from. Now, the reason I'm bringing this to you as an astronomer, and the reason I got involved in this as an astronomer, is that I would argue, and I hope you're with me on this, that as astronomers, we have a pretty front seat view to a lot of things that are known to invoke awe. And I don't want us to ever take those for granted. And I think it's often seen as like a tangential benefit of the work that we do. But what I want to argue to you today is that we need to center it in a way that we don't normally center it for all kinds of reasons. Okay, so here comes a quick teaser. Obviously, in the next 5 minutes, we're not going to go into details on any of what follows, but I just want to give you a sense of what's out there and the references if you want to follow up on any of it. Okay. Here is a study that talks about how awe enhances creativity. In this particular psychological model, there are 4 dimensions of creativity. These are those 4. And when we look at how people respond to things in these 4 dimensions of creativity, when they are in a state of awe versus in a neutral state, all 4 of these are enhanced. Again, I'm throwing a lot at you, but I just want to give you a sense of the data that's out there. We can also look at how experiencing awe impacts people's ability to understand the scientific method. And look at this, right? So the correlation between people's ability to understand the scientific method is hugely impacted when they are in a state of awe. It's also negatively impacted when people aren't. I guess if you're happy, like you don't care how or why things work, right? You just kind of accept them. And so, some of that makes sense. You can see some anti-correlations here, some very low level, I would say, not correlations. So for example, whether or not you're experiencing love is kind of neither here nor there in terms of how you view the scientific method. But experiencing awe is really important. Okay, share with you just a couple more quick studies. This one has to do with how people digest the strength of different arguments logically. I'm not going to go through, because we don't have time, what a weak argument is and what a strong argument is, but I think everyone in this room would recognize them, especially if you pay any attention to political discourse. When you experience awe, and I've highlighted these in orange, your ability to to recognize weak arguments and strong arguments is much, much, much better. And I actually really do think that's existentially important for the future of humanity. So another thing awe is known to do is promote humility. And this totally makes sense, right? Because if you are trying to put in your brain things that are so vast you can't get them into your mental schema, you might think of yourself as maybe not being so godlike as you did before. And I am a fan of, I realize some people are just naturally more hubristic than others. I would like to think that we try not to be, but I think humility is really important in sciences, because if we're not honest about what we can do and what we do know, how do we make progress? And so I think humility is really important. Humility, then, it turns out, is actually really important for cognitive flexibility. And cognitive flexibility, I would argue, again, is really important for science, because how do we make progress if we're not willing to change how we think about things? So bringing this back then to the importance of sciences, there was a whole thesis on this about, I guess, more than 5 years ago now, where what the student did is they went out and they interviewed a whole set of people in natural sciences about their experiences, and they were looking for, in the way social scientists do, impacts of awe. And I want to share with you a couple quotes I pulled from this. Really, it's a full thesis that may or may not resonate with you. Okay, so participants lamented the demands to publish and the importance of pleasing funders as limitations that prevented them from pursuing projects that fulfilled their sense of curiosity and would have the potential to evoke awe. Anybody? Okay. Several participants also pointed to a sense of competition that dampens their sense of awe, especially in the context of awe that they might have otherwise felt in response to someone else's success. Okay. So I have a bunch of working hypotheses that I'm going to share with you that in sort of my side life I'm trying to pursue at some level, which is intermittent at best. But I do have some working hypotheses that I think are true and I'm hoping to be able to test that I want to share with you. I suspect that awe encourages science as a career. And this is a great social science experiment that I'm working with folks to try to do. I think it's probably going to promote healthier collaborations and inclusion, enhance teaching and mentoring, improve science literacy, which is, I think, something we probably care about. I also think it's going to help with burnout. I don't know if any of you all have ever felt burnt out at any point in your career. Okay, thank you for laughing. I feel like awe has got to help with that, right? Remind us why we do what we're doing. Okay, so I'm going to end. I realize this is super rapid fire, and I'm trying to end on time and be respectful of everyone else. I do want to end with one final quote from that thesis as really, I think, a call to action and something I hope we can all sit with and think about. So this is a direct quote. I think that for the vast majority of scientists, it is about surviving in something that has lost a lot of its meaning and has become just something as marketable as anything else. We're fighting to publish so that we can survive and get grants. At the end of the day, science is not anymore a place of awe. Research is a place of struggle. And I would argue that that's not what we want it to be. So I'm going to stop there. I hope that I've given you enough of a teaser that you're interested and that you will try to center awe both in your own lives as scientists, but also in your teaching and your interaction with people. So I'll turn it back over to you, Avi. Okay.
Thank you so much, Kelsey. As far as I'm concerned, you are preaching to the choir.
Excellent.
But one comment is that in astronomy, very different, let's say, from experimental particle physics, we have the universe as a source of awe, much more so than our colleagues. And in other disciplines, especially those that are dealing with abstract concepts, you need to sort of look around who is working on it and calibrate yourself relative to others. But in our case, you have the universe, which is an amazing source of awe because there are phenomena that we don't encounter here on Earth, and they are far bigger than we ever experienced that could actually satisfy your narrative in the sense that we just need to be modest because we see the rest of the cosmos, right?
Yeah, I think we obviously have a super special place as astronomers. I would also argue, though, there's room for awe in everything. Like, I will literally stop on a hike in the woods and marvel at the fractal structure in a leaf, right? Or, if we think about math, I'm pretty upfront about this, though I've not yet gotten the tattoo. Euler's equation blows my mind, right? There are things, I think, no matter where we look, if we actually try to look at it through the lens of what could we experience as being conceptually vast, even if it's an equation, I think it could really open things up.
Just don't tattoo the dark energies of cosmological constant, because Desi argues otherwise now. So.
I'm not touching that right now. No. I'm going to wait for that whole thing to settle down.
Okay. Comments, questions? Yes, please.
So thanks for that, Kelsey. I wanted to point out that there's a beautiful book, you probably know about it, by Rebecca Elson. Do you know it? It's a book of poetry, astronomy poetry, and it's titled A Responsibility to Awe.
Yes.
Which I think is a beautifully titled book of astronomy poetry, and I encourage it.
Thank you. Thank you for bringing that up. All right, I will sit down.
Is there anyone that disagrees with the theme that
No, I just want to know how long does the experience of awe last?
Oh, that's actually something we're working to test, because you can test a dispositional state that you're in after you experience awe. It depends in many ways on how strong the experience was. It also depends on how much you reflect on it after the fact. And so there are lots of factors that fold into it. We've found that you can still see impacts of awe at least up to 2 weeks out, but it does have a decay time, right? For most people, of course, there's variability. So it is actually a really open question that's really interesting.
Yes, please.
Can I follow up on that
Yes.
point, which is, what do we know about, I feel like there's an element of when you familiarize yourself with an idea in this decay time, we use numbers in our work like 10 to the 15, 10 to the 18 all the time, and I don't actually think about what that means, right? I just use them.
You're totally desensitized.
Exactly. And so is there thought about like how explaining that to other people can reignite that or
There is a lot of thought about that.
There's astronomy as a social activity, part of that is realizing something but then sharing it.
Yeah, there's a lot of finding things we take for granted and not taking them for granted. There is also, though, the flip side of this is that a part of awe is the need for accommodation. And, you can become desensitized to things because you have accommodated them, right? So there is kind of a flip side to this that, maybe a fractal structure in a leaf causes me awe once, but by the 100th leaf, I'm like, eh. I actually just experienced this last week. I had my family in Iceland. It was bucket list trip to bring my kids to see the Northern Lights, and they're like, eh.
Amazing.
Another direct follow-up to Alyssa's question and maybe to our conversation earlier today. I'm wondering now how you actually measure.
There are psychological surveys that measure, try to, right? You can't actually get in someone's brain. Well, let me revise that. There are fMRI studies where you can measure parts of the brain that respond to awe, but you have to do that when someone's sitting in an MRI, which makes it hard. But there are also dispositional studies that have been developed, inventories that have been developed by psychologists, and part of the work right now is trying to align the dispositional inventories with what you can actually see happening in the brain. And part of the work happening now is to see if we can induce states of awe in an fMRI via things like augmented reality, but it's hard because you still don't have that full multi-dimensional experience.
So dispositional inventory means facial expression and things like that, or elevated blood?
It's much more simple than that. And I'm actually kind of embarrassed to share it. There's a questionnaire you can answer that has to do with how small or big you feel with respect to things, and there are a bunch of different elements out of it, but it's literally like a questionnaire.
Oh.
Yeah.
Kelsey, since the ITC...
All right, we need to stop.
Since the ITC is a center for theoretical astrophysics, just a question. Do you think that, when we face a phenomena we don't understand, we will have awe, but then if you have a theoretical understanding of it, does it eliminate the awe, do you think?
It depends on how you feel about that theoretical understanding. I mean, maybe that's vast, right? I would hope. Let's not be overly prescriptive. Let's be generous about and capacious about how we think about awe. How's that? Okay, I feel like we are way over my time, so I'm really going to sit down.
Okay, so first, thanks for giving me this opportunity. So I will try to speak up.
Do you have the microphone? Maybe?
Okay. Okay, so I come from Shanghai Astronomy Observatory. So I will present some work we done with in collaboration with some colleagues from Cambridge and the University of Luque. So it's primarily about modeling subsonic turbulence, but with meshless method. Okay, so we all know that turbulence is very common in astrophysics, especially in accretion disks. So there's a very famous magnetorotational instability. So if you have some accretion disk around a star or around a supermassive black hole, if it's threaded by some magnetic field lines, so give it some perturbation. So then the magnetic field line will act like some string. So it will pull the inward perturbed fluid parcel and give it some outward drag. So it will decelerate it, and then it will lose angular momentum further. So it will spiral inward. So this is a runaway process that will produce exponential growth in the magnetic field, and eventually it will saturate some turbulent state. So there are some, it's already well studied in the community and with many grid code simulations like the global MRI simulation with the finite volume method, the Pluto code. But it's very difficult to do with meshless method. So first, it's well known that if you do it with meshless method, you cannot even sustain subsonic turbulence well. So if you have some driven turbulence and with some meshless method like the traditional smooth particle hydrodynamic method, which is called SPH, so you'll find that the turbulence is damped, and you cannot resolve the fine structure like the simulation by the moving mesh method, aka here the Aripo code. This is primarily due to the numerical noise and also some inaccuracy in the gradient estimation, so you can find more details there. But today I will focus on a classical method called meshless finite mice. It's in the Gizmo code. It's pretty much similar to the Aripo code, but you do not have a real cell. You do not have the tessellation, but you have some abstractly defined cells, effective volume, okay? So we have applied the MFM method to MRI simulation in a local approximation. So basically you cut out a patch of the disk. It's called a Sheeran box, and you focus on the flow in the box. And if you do it with SPH, you find more or less you can capture the turbulence in the magnetic field line strength. But if you do with the MFM method, you can resolve better the finer structure, and you have less noise in the field strength plot. More importantly, we found that if you do it with SPH, after a certain amount of simulation time, the flow is damped out, likely by the artificial viscosity, and you get some strong toroidal field, very strong, and it's totally unphysical according to our experience with grid codes. So we want to caution you that if you do with SPH, MHD simulation of accretion disks, you get wrong results sometimes. And we went on to do some global simulation with the MF method, some of the highest resolution single disk simulation of global MRI. And in the middle panel, we show some other simulation, which consider also the self-gravity of the disk. The disk is relatively massive, and it's gravitationally unstable. And you see that in the field strength plot, you see this kind of large-scale spiral structures, which are imprints of the global spiral density wave. And it hints that the background spiral density wave is powering the magnetic field growth and amplification and sustainment, okay? So it's like you have a cup of water, and you play a straw in the water, and you stir the water with your straw. So you have some way to inject energy into the accretion disk flow. So that helps you to sustain this kind of dynamo, and we call it spiral density wave dynamo. It's totally different from MRI. And in terms of power spectrum, we have done a lot of convergence tests, and also we affirm you that we can resolve a very high azimuthal wave number up to or beyond 200 in the azimuthal wave number. Okay. And finally, so the disk may fragment. I think some people are familiar with the concept that if you have gravitational unstable disk, like in the context of galaxy, you have the spiral density waves. If it fragment, it may form gem or molecular cloud. In the context of protoplanet disk, if you fragment, you may form protoplanets of Jupiter mass. But here we found the interesting that in the presence of magnetic field, once you fragment, your fragment or clump will be wrapped up by very strong magnetic fields. We call it magnetically controlled fragmentation because the magnetic field, in terms of energy, its magnetic pressure is stronger than the gas pressure, and it also dominates over the random motion of the flow in the vicinity of the clump. So that gives you a way to form very low mass fragment. In terms of planet formation, you may have a way to form directly where the disk fragmentation of Jupiter or planets as light as Neptune mass. And the magnetic fields not only prevent it from growth, but also protect it from disruption by the turbulent background flow. These are some simulations. We tried very hard to simulate magnetized flow with Meshless method. It's painstaking, yeah. And it takes my whole PhD to do that. But actually, there are some comfort zone or advantages of Meshless method in simulating subsonic turbulence. It's primarily lying in the context of distorted disk. So when I talk about distorted disk, first there are some warp disk observation in the context of protoplanet disk. So these are some dust continuum emission observed in around this very young star. And if you do it with a grid code, you'll find that your disk will change in inclination, and also it will change in its longitudinal precession, longitude of ascending node, sorry. So this is because you have this kind of warped geometry in the flow, and that will have some misalignment between your grid and your flow. So this will always give you some trouble in this kind of finite volume method, or we call it advection error, that will leads to this kind of unphysical evolution. But if you do it with a Lagrange method or Meshless method, you don't have this kind of worry. So it's well known that in this kind of warp disk, you have some delicate instability, hydrodynamic instability, okay? So if you have a warp disk, and this is just a schematic plot, you can cut away a box of flow in a local point of view. If you stand on this box, it will revolve around the center. So it will experience periodic change in its environment. So if you rotate around for one circle, and then you will restore your previous state. So that means, imagine you have a box of water. You are turning the tank of water back and forth. So you will stir some waves in this kind of bottle of water or tank or box of water. So it's called parametric instability. And some people have done some theoretical analysis and some local simulation. Basically, you focus on the flow in the box, and you can find turbulence. But it's never done for a global simulation. In global simulation, you can rarely find this kind of instability. Because if you do with the grids, you have the advection errors, and it's also difficult. So we have done some simulation with the MFM method I mentioned, and we found that in terms of the, here we plot the Mach number of the flow, the velocity fluctuation. You see that after a warp propagates away, and it will leave some turbulence behind it. So we find that the warp will be quickly damped by this kind of turbulence. So it gives you a way to damp out the warp, and it's a very generic process. Basically, it's associated with the warp itself. This can be measured in terms of the angular momentum deficit. It's a measure of how strong the warp is. We find that it damps very quickly because of this intrinsic turbulence. And another example of a distorted disk is the eccentric disk. We know that if you have a star passing by in the vicinity of supermassive black hole, it will be tightly disrupted. And people are mainly focused on this kind of early stage. People think that there was some stream collision and also some nodal shock that will kind of circularize the eccentric disk. But actually, if you look into the simulations, at the end of the simulation, you still have some residual eccentricity, okay? So with eccentricity about 0.1 or 0.4, between that. So we'll find, we still have this kind of parametric instability because from the mechanism I mentioned, you revolve around the central star and you experience periodic change. And also you can have some instability in this case. I will carry out some global simulation of eccentric disks. We confirm that, so you can see in the density plot, you have some fine structures in the density field. So these are another kind of instability in very generic in eccentric disk. Okay, the movie does not play. Anyway, so this is a cutaway plot along the x-axis. Just show the phi equals 0 slice. There will be some wave activity. Yeah. Finally, I will just show you a movie. We also do a moon-forming giant impact simulation. Basically, you have proto-Earth hit by a Mars mass object. So this treats the materials. You'll find that after impact, the proto-Earth will have a layered structure in the middle mantle. This has some implication for the evolution of Earth because there are also some present-day middle mantle stratification there. Yeah, we're trying to make some connection between the very early on impact event, 4.5 billion years ago, and right now. Okay, thank you.
So, Hongping, protoplanetary disks may not be ionized throughout.
Yeah.
There is the dead zone,
Yeah.
and obviously the ionization is necessary to couple the magnetic field. And so when you mentioned Neptune mass planets made this way, I mean, what sets the minimum mass actually, or how do you get? Did you assume that it's fully ionized, or?
So first I want to mention that. So this process is not sensitive, not so sensitive to microscopic non-ideal energy effect, because you have energy injection from spare density wave. So we have, if you add some ohmic dissipation, that is enough to kill MRI. It's not enough to kill this kind of spare density wave dynamo. And in the simulation, we have only taken into consideration the ohmic dissipation, not the two other terms. But anyway, so we think we're working on that. We're improving to include the non-ideal effect. But we think it's robust. Okay.
So how low can the fragments be? How low mass?
Oh, okay. Neptune mass.
Neptune. You can't go to the mass of the moon, for example.
No, not really. Yeah, because you. It's really the balance between the gravity and the magnetic field strength, and also the gas pressure. Yeah.
Okay. Any comments, questions about the many aspects of the work that we heard? Looks like everything was clear, and then the work is fascinating. Thank you so much.
Hello, everyone. My name is Rafael Luque. I'm a science fellow at the University of Chicago. Thank you very much for the opportunity to be today here presenting this project. So related to the previous talk, the fact in the exoplanet field that produced me the most awe is this sentence, which is that the most common type of planet that is discovered to date, out of the thousands of exoplanets that have been discovered, doesn't exist in the solar system. So 10 years ago, Kepler revealed that planets between sizes of Earth and Neptune, they are the most common at short periods orbits, typically closer than Mercury. This type of planet exists kind of in every other star like the Sun, but we don't have them in the solar system. This bimodal distribution, also known as the radius gap, has led to the definition of these two types of classes of planet. the ones that are slightly larger than Earth called super-Earths, and the smaller than Neptune called sub-Neptunes. So the community agrees that super-Earths are kind of larger versions of our own planets, but for sub-Neptunes, their properties remain a mystery. There have been two main hypotheses that have been proposed to explain the internal structure and the origin of these sub-Neptunes. The first and most common interpretation is that these sub-Neptunes are something called like gas dwarfs. It would be a rocky core surrounded by large hydrogen atmosphere. They are assumed to form very close to their stars where they accrete primordial gas, mostly hydrogen, that is devoid of volatiles. But there is a second hypothesis which has gained more momentum recently, which is that the planets are water worlds. Water worlds are something akin to comets or other icy bodies in the solar system, and their total mass fraction in volatiles, mostly water, may account for 20 to 50% of their total mass. Their internal structure is heavily discussed, as you can see in this diagram, but it is clear that in order to acquire those big amounts of water, these planets must necessarily form beyond the ice line of the system and then migrate inward to these present-day locations where we detect them with Kepler. Today, observations of sub-Neptunes are kind of consistent with both hypotheses. This is because to distinguish these scenarios, measuring the planet size as Kepler did, it is not enough. So we can add two observables to these measurements, which are measurements of their masses and atmospheres to try to dilucidate this problem. Mass radius measurements are able to constrain the total bulk density of the planet. But in this part of the parameter space where sub-Neptunes live, as you see here in a mass radius diagram, you can have multiple combinations of iron, water, hydrogen in order to explain the observed quantities. And they all will have very different implications in the internal structure of the planet. On the other hand, we would have atmospheric characterization, which is a very promising avenue. But the set of observations that were possible with Hubble, they gave inconclusive results. And this is because there is an inherent degeneracy when you study these atmospheres in transit between the presence of clouds in a hydrogen-pure atmosphere with an atmosphere fully made of water. You see this banana plot here with the water mass fraction as a function of clouds. And this gives a very similar transmission spectrum in the wavelength range that was probed by Hubble. From a theoretical perspective, there are also some unknowns related to the solubility of water in a magma ocean, which is expected for the interior of this planet. Also, how water mixes with the atmosphere, if there is any hydrogen. So this is probably the most active field of research, I would say, within exoplanet science, or at least one of those. I'm the PI of Thirsty. This is an ERC starting grant project starting this summer, designed to overcome these challenges that have stopped previous studies and try to reach some more definitive conclusions about the origin and nature of sub-Neptunes. And Thirsty, the science questions that drive this project are if sub-Neptunes are gas dwarfs or water worlds, if these water worlds only exist in M dwarfs, as some evidence point out, or also for sun-like stars, what is their atmospheric properties, if we can gain some insight into their interiors, and what if both exist, what would be the relative occurrence, and how does it depend on other system properties? The Thirsty takes an observational approach, it's an observational project, and will collect new data for individual targets using the best telescopes in the world to open parts of the parameter space that can help breaking degeneracies in models that predict different behavior for the gas dwarf and the water world hypothesis. And the project is divided in three main working packages. I'll go very briefly on it. The first one is atmospheric characterization, and for this, the workhorse is JWST. JWST has demonstrated to have the sensitivity and the broad wavelength necessary to study cold sub-Neptunes for the first time. This is a clear example of K218b. It shows what is JWST capable to do for the first time. There have been studies recently focusing on cold to warm sub-Neptunes orbiting M dwarfs. There is a tentative trend that there is an increase in the volatile-rich content of the atmosphere as a function of temperature. You see how these features shrink as a function of temperature. These planets are hotter and these are colder. The hotter the planet, the higher the mean molecular weight of the atmosphere and its metal content. That makes the detection of this species much harder. But we hope that with these new programs in cycle 3 and 4 that I am part of, to explore if these trends holds for much hotter planets and what is the effect of clouds and hazes in this degeneracy, if maybe not play a role or it does play a role. And also we want to explore the age dimension, how atmospheric metallicity evolves with time. Even though there is a lot of community interest in sub-Neptunes, these are the only JWST programs that have been approved this cycle on this topic. Another central part of the work of Thirsty is the measurement of ball densities using radial velocity instruments. And here, it relies on the resources that I've been securing for the last 2 years. This includes more than 650 hours of telescope time in some of the most important radial velocity instruments in both hemispheres. And we'll be able to double the sample of subneptunes that have measured densities that are also amenable for atmospheric characterization. Their stars are good for JWST. The sample definition and the first results from this sample were presented in this paper from late last year. And one of the key features of this sample is to extend the range of subneptunes with measured densities across all planet temperatures and also host spectral types. Why is this interesting is because there are theoretical predictions of how, from planet formation and evolution models, that they expect different behavior in this different distribution in mass radius space as a function of these parameters for gas dwarf and water wall hypothesis. All this observational work will be complemented with a new demographic and statistical analysis, and the idea is to extract population-wide conclusions from the observations in these previous working packages. So we aim to correct the observed sample from detection and selection biases of both the transit and radial velocity technique, and this will be done also with the help of this new formalism that we have developed with my colleague Hannu Parviainen to model populations in mass radius space with this code called Sprite. Just to sum up, I would like to stress that subneptunes must be studied now. The timing is an important piece, and this is because we need masses, we need radii, we need atmospheric measurement just to get started with their characterization. And right now, we have all the facilities necessary to do that. And we are planning to move on from this type of planets in the future to focus on Earth analogs. So this is really the time to do subneptunes. And there is an important pair, which is if subneptunes are indeed water worlds, that will change obviously, it will change our view of the most common type of planet we know in the galaxy so far. But it can also accelerate the search for extraterrestrial life because subneptunes are larger, they are more abundant, they are easier to detect, they have larger atmospheres than terrestrial planets. So this is why the title of the talk was the water wall opportunity. So I think water walls really could extend habitability searches to the most common type of planet in the galaxy, and a type of planet that is more favorable observationally to characterize than terrestrial worlds. So I'm happy to take any questions. Thank you very much.
Thank you, Rafael. Just about your last comment, obviously the chemistry of life is in liquid water as we know it, but if you don't have rock, you can't really have ponds that dry up and concentrate chemicals. So some people argue that you need an interface between rock and water. So do you think just water is sufficient?
I don't think we need to think about these planets as a liquid water ocean type of planet. We need to think about these planets as having a magma ocean which is much lighter than if it would be made fully of rock. So what we are thinking is, what if you put a comet, make it supermassive and put it close to your star? It would not necessarily lose the rock. You are just having a magma ocean from the properties. You can add a lot of water on it and still not change its properties. So I think there is room in the modeling for still being able to have tectonic activity, to have layers, to have a separated interface between surface and atmosphere. And you may have an atmosphere very enriching water and a magma ocean very enriching water, but maybe it looks more like a super in terms of what we are thinking on it. So I think there is a lot of theoretical understanding and modeling that can be done to test that hypothesis.
When you talk about the magma ocean, it should be at a temperature of 1,000, 2,000 degrees. So
yeah,
that's very hot. And on top of that, you put the water?
So you'll have the water in it.
In it?
Yes.
Okay, so it's saturated with water,
exactly.
But it's still very hot, you're saying.
Yes.
It's like...
So you need to explore, obviously, these Kepler subneptunes, which are very close to their stars in very short periods. They are not good candidates for this type of life environment. But the ones that are farther away, you can have a stratification in which you can really have suitable conditions at the surface. I would say we haven't probed the coldest subneptunes that could be really good candidates for habitable conditions yet. But I think Plato, for example, is a very promising avenue because it will really explore again long transiting planets that we can measure the radii, their masses and everything precisely, and will be much colder than what, for example, TESS has been recently detected.
Thank you. Questions, comments, Eric?
So how would you form a water planet? I'm thinking because that spectrum that you showed from JWST, those are all carbon molecules, methane and so on. And so we don't have a water planet in the solar system. So why would there be, what's the difference between?
So the protoplanetary disk beyond the ice line will be very rich in ice, water ices and rocks. So there will be a lot of material available beyond the ice line of the system to form planets that have an enriched water content. These planets, the only problem is you need to migrate them in to compare them with what we have been observing, because we are not sensitive to detect them at those distances. So when you heat up the planet by migrating it closer, it is when this process is starting to make more sense, and you can put some water into the atmosphere in the form of steam and things like that. I think it is not about a water wall in the sense of having a liquid water ocean. It's just a planet that maybe looks more like a super Earth or something like that, but will have a lot of water available, especially in its atmosphere and its interior. So all those interior atmospheric reactions will have water available for this type of conditions. Anyway, water walls were the first proposed explanation for super Earths. So it has been a product of planet formation and evolution from the very beginning, because if you think about forming planets all across the disk, beyond the ice line there is a lot of water ice available. So when you start accreting that into a planet, you could have a body similar to a comet or an asteroid, which will be very water rich.
Could you also get it just from comets, the way Earth got it, like comets delivering much more?
I mean, the amount that you need from bombardment, it would not make up to the mass fraction that we were talking at the beginning. That's why we are talking about these water walls. I would say a reasonable definition for them would be really that they have formed beyond the ice line. So necessarily that water content in the planet cannot be explained by comet bombardment, interior atmospheric reactions that can create some water and things like that. I think that cutoff, putting it above 20% in terms of water mass fraction, really pushes it to be only from formation.
Please.
You argued, I think convincingly, that you're looking at the best combination, these reasonably massive stars and the reasonably massive planets around a smallish star, but still the star dominates the emission big time. So what are the constraints on the stellar atmospheres? Do we know enough? Are there well enough constraints to really decipher the last bit of information?
I think our understanding of stellar models for the purpose of atmospheric characterization, mass characterization, radius characterization is good enough. I think the understanding of stellar activity, which normally makes these complications, these observations that are already degenerated, even more complicated, that is the part that I think there is a lot of room to improve. Especially in the case when you study these sub-Neptunes orbiting endwards, the stellar activity becomes such a problem that your observation, what you are trying to measure, is really hindered by the stellar magnetic activity. I think for sun-like stars and the few sub-Neptunes that we can do orbiting sun-like stars, our understanding of these stars are much better, and we'll be able to get, with these new facilities, really good constraint. But in the case of endwards, stellar activity and our understanding of stellar activity, it is crucial.
Any other comments? If not, let's thank all our speakers today.